This is a voiceover from German to English. In the foreground you see me, in the background you see my machine, a Tesla Coil winding machine. It has all the parts which a CNC machine has, and it's controlled with a microcontroller STM32F4, which is powerful, and on it running is MIOS. This is a real-time operation system, and it's a good choice. Good. With this you can save and load patches on the SD card, and you can make the same coil over and over again with different models, and you can choose between them and so on. The video has two parts. The first part is you see the winding machine winding and how I fit the wire in and so on, and the second part is a time lapse of the build, where you see from the beginning to the end building the device in a very fast way. Have fun. Connect 5-volt power to microcontroller. I start now any program. It goes to the home position, to the 0 point. It finds it with a micro switch, which is activated now. It drives now to the start position, which is pre-programmed from me. Now I say go forward with the program. Now I take a 150 sandpaper to rough the pipe. I start now the program. First it finds the 0 position again. Now it drives to the offset. The offset is the beginning of the coil. Paused until a button press to resume. First I have to fiddle in the wire. This is a copper wire with 0.2 mm diameter. Fiddle it in V-groove rolls. The motor now is braked, so it's move hardly. That's a good thing. The wire have a overlying, so I can make a node. This will be our start winding stage. Take isolation tape to fix the wire. I will leave the tape there, it doesn't hurt when it's there. After pressing start, it will make a 10 mm start isolation winding stage with maximum feeder move. Now it's slow again with 0.2 plus a minimum offset of 0.1 mm from winding to winding. The mass is correct and the coil should be about 270 millimeters long. And if the wire is long enough, this should fit on the pipe. Hopefully. The display indicates how many meters are needed for this pipe with a diameter of 40 millimeters. I can pause every time, which I will make now, because I noticed that it's not running round. I have too much force on the pipe, so I have to release the mount a bit, so it runs more even and we have less tolerance between the traces. Press start again to resume the operation. You see, this is not optimal. This should be machine milled mounting parts. This should be very precise. This is not. Also the pipe. I've cut it with a handsaw. This was not a good idea. But it don't overlaps. I have an offset of 0.1 millimeter between the traces, which are itself 0.2 millimeter traces. So this can be optimized so the length of the coils could be reduced in future. On the display in menu 2, it shows you that we are on turn 239 and we are on the stage norm wind, which is the main part of the coil where all hundreds of windings are. I hope I have enough meters of wire and enough space on the coil, because this is the first real test with copper wire. Before I have tested it without this, because the wire is expensive. Here I've taken a wooden block, I drilled a hole, filed it out so it don't scratches the paint of the copper wire. Here are 4 rolls with 4mm screws and reverse mounted stop nuts so they don't break. The mounting plate is all SSD drive, where the top plate is mounted first and the bottom plate I use to mount all my rolls and things. This is an old mic stand. It's all a bit loose, but it doesn't matter. Okay, we are on the end of the wire and the pipe is not finished yet. So we have to break the turning. No. Stop it, yeah. We have 681 turnings. So the wire was not enough. The coil haven't enough meters. I have to fix now the wire on the pipe so they don't loose anymore. So cut first. Enough strange on the rolls so it don't move away. so some isolation tape to fix the normal winding and to make some isolation windings. Because when you mount a top load on the pipe, the metal, it can make sparks because of the potential difference, and this is less when you have a high chain between the windings. Yeah. Isolation tape again to fix this. (681) secondary windings divided by 2 primary windings is a factor of 340. Multiplied by the PSU of 24 volts gives you 8 kilovolts. When you use 34 volts, for example, or 35 volts, you get a secondary voltage about 12 kilovolts. This coil is 20 centimeters long, 1 centimeter isolation start winding and 2 centimeters isolation end windings. I used a 12 millimeter spindle here and a 1.2 ampere motor with a movable area of 450 millimeters. The turner itself on the background is a bit short with 30 centimeters or 35 centimeters. This could be optimized in future to get about 39 or something. The turner in the background has a 8 millimeters spindle, and this is not good. This should be also a 12 millimeters because it bends, and it should not bend. I have made this wood thing on the side so I can remove the pipe again, and on the spindle mounted is this wood block which has this nut on it, so it can be fastened together. On the backside, 2 microstick drivers DM542 with a stepping of 400. I use it 1-to-1. The good thing about them, they can deliver 4 amperes and they are supplied with this 24 volt 10 amp PSU. The good thing about them, you need a direction signal on one pin and a pull signal on the other pin, and they toggle, and that's all about it. Easy to program. 3 input pins enable direction and pulse. Then you have the supply wires from the PSU and the coil windings wires to the stepper motors, and that's all. On the microcontroller side we have this digital EO board which is connected to the user interface where the buttons and encoders are. Also the displays which are directly connected to the microcontroller. Also on the digital EO board is a direct connection to the microcontroller's GPIO pins, which has 3 volts and which are level shifted here to 5 volts, which are needed for the motor drivers optocouplers to work. The microcontroller itself is a STM32F407, where MIOS is running. MIOS is a FreeRTOS based MIDI operation system, and more information about this and the code you see in the description of the video, and how to build it, a wiki and so on. On UCAPS.de you find a wiki section where you can search for different projects, for example the Coil winder, where everything is documented. You have here the source code, the firmware, and the bootloader, and the program to upload the bootloader, some schematics where the digital I/O is on and the connection to the motor driver and so on. Main parts are used here for the hardware. These are just examples, but these are the ones I used. And also a bit overview about the menu structure, where you see what settings you can turn in at the moment, and some results. These are the winding stages. Yeah, that's about this. But in order to get a real overview how the MIDI-box platform works, you just have to go to the ucaps.de and have the focus on the microcontroller board, which is this. And also you can look at the schematic to understand what's going on. For example, when I'm on the Coil winder and there is a digital in, digital out connector or a display connector, you will find the pinout of this on the schematic. For example, the display connector is this one, and the digital I/O is this one. It's the pinout. And you also have the GPIO pins, which are connected with a level shifter, which comes after this, from 3 volt to 5 volt, because this is a 3.3 volt device, the STM32F4. Yeah, and some additional things is, for example, the digital input module, which is a multiplexer circuit, which I also use for the user interface, where I use 3 of these registers. And you also have something to do with the bootloader. Because you get a Virgin Discovery board from your supplier and you have to upload some code. There's inbuilt a JTAG programmer. You just need a USB cable to upload a bootloader, so you can upload my code, which is here, the firmware. Yeah, that's all about this. There's also a forum, which is commonly used for MIDI-box devices and audio machines based on microcontrollers. And this is the forum where you can contact me or ask or feel free for add-ons and so on, your modifications. And the source code is also on there, on the firmware. the main thing you have to do is make things in app.c. Have to change their things if you want to change things. And this is the compiled binary, the hex, which you just have to upload, and it will work. When you want to change the code, you have to go to app.c, change the code, and rebuild this thing, and the result of the build is the project hex. But this is another story, a long story, because there is a toolchain that you have to install, like on all other microcontrollers, and it's a bit of work to get this running. Good. Have fun with this happy build, and on the next stage of this video you will see a time lapse of the hardware build of this device.